Hello, everyone, and welcome to Coffee with CALEFFI. Glad to have you on board. This is Mark Olson coming at you from sunny Milwaukee today. I'll be your host and presenter. Bob Hot Rod Rohr is up in central Wisconsin at a Midwest Renewable Energy Association fair, and it looks like you'll have a good day for that, given that solar will be one of the topics of interest up there. Today marks our 50th Coffee with CALEFFI. I just checked that out just a few minutes ago. If I had to guess, I would have said 30 or 25, but time flies. So all of you that are new on the call, and it looks like there's quite a few looking at the list, we're recording this webinar, and it will be available to you after a few days in our archive where you can reference all of our other prior archives. So that's a service to you. So we'll get going here. Today we're going to talk about air, dirt, and pump conflict. Three gotchas in hydronic system design, whether you're doing geothermal systems or solar thermal systems or just straight up radiant systems. The issues of air, dirt, and pumps not working together in a friendly way are very common, I call them gotchas for the designers out there. So I want to start off with a slide just talking about hydronics in general and, some of the benefits of hydronics and walk into air and dirt. Why do we love hydronics? Well, you can send a lot of heat from point A to point B by way of hydronics as opposed to, as an example, by way of air. And in doing so, also, we don't have to be so invasive with running heat from point A to point B in a building. So it takes a lot less, construction to route heat using hydronics than air as an example. So as an example, here's a shot of some duct work, very invasive, if you will, as opposed to a hydronic system. So hydronic systems are efficient from that standpoint. They're also very efficient from the standpoint of how much electrical energy it takes to distribute that heat throughout the building. So pumps, as an example, consume significantly less heat versus in a fan system, a fan doing the same thing. And that basically boils down to the properties of air. Air is compressible, and it's not so efficient to get air to move from A to B in an effective manner versus water, which is relatively, well, basically incompressible, and as a result, pumps can be applied, and basically heating or cooling our building can be done very efficiently. Now, when we design a hydronic system, and here's one in front of you, some things that stand out. First of all, the effects of air. We have a couple of automatic air separators you can see over here. And so the question is, how do these work? Where do you apply them? Where in the system does the engineer put an automatic air separator? They're meant to operate under pressure and expel air as it builds up. But can they bring in air or suck in air into the system and cause problems? We'll talk about that. Expansion tanks. I don't know too much about this job. I don't see an expansion tank, but if I look over here, I see another air separator and something connected to it. And knowing that expansion tanks and air separators like to live in the low pressure side of the system, I'm going to guess on the other side of this wall is an expansion tank. So where do we put our expansion tanks to allow the system to be most effective? What happens to an expansion tank if it becomes ineffective, if it becomes waterlogged? What does it do to the performance in the system? What if we took this isolation valve here and isolated the expansion tank? What's the effect of that, whether it's done on purpose or accidentally? Looking down below here, I can see a flat plate heat exchanger. I don't know. My guess is this is a snow melt system. And perhaps on the loop side of the snow melt system, because we're in cold weather when you have snow melt, you want to use antifreeze. So perhaps the contractor used a propylene glycol type antifreeze with inhibitors. What if he puts, mixed with that, instead of having conditioned water, straight up well water? What are the problems and implications of doing so? I don't see any dirt separators on this job. Perhaps there is. Perhaps this is new construction. It wasn't so much an issue. But what happens if we have corrosion in our system? And basically, the effects of that corrosion causing debris to get into, well, it could get into our heat exchanger. It could get into our boiler. If this is a cooling system, it could get into our chiller. What are those problems? Pump conflict. There's a couple of pumps over here. Hopefully you can see those okay. those are meant to act independently of one another. If one pump turns on, it shouldn't affect the flow rate being driven by the other pump, and vice versa. They should be decoupled. So how do you apply the piping and design the piping to make sure you don't have pump conflict? And lastly, we can see some variable speed, electronically commutated motor type pumps over here, very efficient. Okay, what about those? They're excellent for reducing the energy cost of sending heat from A to B in a system. But what are some precautions as it relates to ferrous oxide and some of that very fine dirt that can get into a system or basically get created in a system as a result of corrosion? So we're going to start with, of the three topics, dirt, air, and pump conflict, dirt, and discuss, well, first of all, where does air come from? Well, dirt come from? Well, it could come from the fabrication process on site. We might want to cut some threads in our pipe, which is commonly done, create some shavings. Those could get into the system. Pipe tape, pipe string, pipe dope, other materials could get into the system. We've seen those here back at the offices in Milwaukee on products that are returned sometimes. The soldering process, you can end up with solder in your piping. On the commercial jobs, you can actually get some weld slag into the system. Well, none of these are really dirt. Probably it should be you don't want it there type slide rather than say dirt. But even real dirt could be an issue. Here's a shot from Dulles, Santa Fe. This is actually dirt. These contractors are fusion welding some geothermal pipes, creating a manifold on that geo system. And if you've been out to geothermal sites such as this, you know they can get dirty and muddy, and the chances of dirt getting into your system are very high. Now, does the designer have to be very concerned about this? Well, not necessarily. It needs to be knowledgeable, because the process of commissioning a system entails purging and filling the system so that any debris largely gets basically rid out of the system. But not all the time. Sometimes it could get hung up in the system, and devices such as, in this slide, dedicated dirt separation devices come into play to protect the very efficient heat exchanger perhaps on that boiler. We'll come back to these dirt separators. But the bigger issue as it relates to dirt is when the system's up and running, everyone's paid, and they walk away from the job, and the system's going. So what happens on an ongoing basis? Well, dirt can form by limescale buildup is one form of basically called dirt. It shouldn't be there. Galvanic attack, and the classic case of rusting or oxidation of metals. We're going to take a look at each of these at a time about what causes them and how to steer around them. So starting off with limescale as an example. In front of you is a flat plate heat exchanger that has suffered the effects of lime buildup. This is a section taken out of the heat exchanger. And the thing about limescale, first of all, it starts to plug up the passageways, so the pump starts to operate less effectively, or basically you start starving that exchanger of flow and thus heat transfer efficiency. And then the other thing is that the limescale is actually an insulator. And so as you start building up, you start losing the effectiveness of sending heat across that heat exchanger, perhaps into your snowmelt zone, or perhaps into your solar thermal, the domestic side of your solar thermal system. Okay? So limescale is an insulator, and this next chart shows you an idea of the effect of the thickness of limestone or limescale in millimeters, and the penalty it has on the heat transfer ability of the heat exchanger. So as an example, we can see as little as 1 millimeter of limescale caked on some type of heat exchanger. This could be your chiller, it could be your boiler, it could be your otherwise heat exchanger. 1 millimeter can penalize you 10%. What does that mean? Well, if we have a 1 million BTU per hour delivery on our boiler capacity, we're now talking 900,000 BTUs per hour, 10%. I mean, I've talked to building managers that would give their pinky for 2%. So why give up 10% with just a 1 millimeter buildup? Now, some designers might say, I don't mind a little bit of limescale because once it precipitates out of water and onto the metals inside of the system, it protects them from further corrosion, perhaps from galvanic attack or even chemical corrosion from air. Well, that doesn't really hold true, because one of the things about limescale is it really is affected by temperature. So perhaps those iron pipes that you're looking to protect from corrosion somewhere down in time, they don't really scale up. It's the high temperature side of the system, typically your boiler in this case, a heating system, where you're going to scale up. And those boilers, those heat exchangers don't like scale. So speaking of such, we'll show that here in just a second, but to give you an idea, for all of us south of the Canadian border, excuse me, who don't understand metric, what is 1 millimeter? Well, there's my finger, and the space between my fingers shows what 1 millimeter is. It's very small, and doesn't take much to get 1 millimeter. By the way, I'm going to go back to that. Franklin Covey, when's the last time you saw that? I pulled this out of my desk the other day. It was part of a Franklin planner that I haven't pulled out in about 25 years, but I still have the ruler. Now everything's done electronically, it seems. So this next shot is what the effects of scale can do, Limescale. So this is a section out of a condensing boiler, a very high-quality condensing boiler that's come to basically Limescale Build Up. This is a fire tube boiler with the section cut out so you can see the effects. So fire comes down, flame comes down into these tubes in a downward fashion, and then in the inverse direction, water comes up. It gets routed by these baffle plates, and basically to optimize the pickup of heat by the water. And you can see the Limescale buildup. And now, theoretically, if this heat exchanger builds up uniformly with Limescale, perhaps might not have had a failure, maybe a heat penalty, but not a failure. But Limescale likes to build up where the temperature is hottest, and the temperature is hottest in this particular boiler at the top before the water leaves the system to go back out to the system, okay? So you have insulation capabilities up there, so the metal is actually hotter up here, relatively cooler down there. Different temperatures on the same piece of metal causes thermal stresses, and that time temperature effect causes what? Basically failure and leakage in this case. So, okay, so what causes Limescale to begin with? Well, the required conditions in a system is that you'd have to have levels of calcium or magnesium in your system, hard water. If you don't have calcium or magnesium, you don't have to be worried so much about Limescale buildup. And acceleration factors that could cause Limescale to form fairly quickly is if your surface temperature is high. As an example, in a domestic hot water system, you could end up with your hot water heater heat exchanger fail because of scale buildup, and then 3 feet away from the hot water heater, you can cut your copper pipes and look at them, and they'll be perfectly clean because they're relatively cool. So surface temperature has a lot to do with acceleration factors. Also, pH level and alkalinity. High pH and high fluid alkalinity accelerate the effects of Limescale. Now, there's a relationship between pH and alkalinity, and we're not chemists here, but pH is basically the measure of acid in your system. On a scale of 0 to 14, 7 is neutral, 0 would be just about entirely acid, 14 very basic. All right, so and alkalinity is a measure of how easily you can change the pH level in a system. So if you own a swimming pool, and you're trying to keep it clean, and you have a high alkalinity, before the chlorine can work, you want to get that pH level down to acceptable level before the chlorine will actually take place. I owned a pool at one time. It's a tricky situation. But you don't have to remember all of that. All you got to remember is high, high, high. High, high, high causes acceleration of Limescale. High, high, high. Maybe it resonates with some of our guys on the call here. Let's jump to galvanic attack, and I'll get back to Limescale in a second here. So what causes galvanic attack? Well, let's take a shot at galvanic attack. Here's a fitting that suffered from the effects of galvanic attack. Now, what's your guess as to which one won the war? Well, obviously it was this T. It's a galvanized T with a brass nipple. The brass nipple is more noble than the less noble galvanized T, and as a result, because the system had the effects of galvanic attack that it could set up, the sacrificial lamb became this T before it outright failed. So what do you need for galvanic attack to be an issue with the system? Well, first of all, you need to have fluid that contains minerals. If your fluid doesn't contain minerals, you don't have an issue. And perhaps the water fill for your hydronic system is going to be taken from a source that is largely surface water. As an example, and that might be without minerals. I grew up near Detroit, and our water was taken from the Great Lakes. As a kid, it was great tasting water. I mean, it had a lot of chlorine in it. I go back there and taste it now. It's not so good. I have to have probably a beer chaser to tolerate it, but basically it was soft water, naturally soft water. So anyway, one of the conditions is fluid that contains minerals. Also, your system, your hydronic system, needs to have dissimilar metals on the galvanic chart. So if your system is largely copper piping and you have a copper tube boiler and everything else is metals very similar to copper, you won't have an issue. And the last thing you need is an electrical conduction path between your metals. Your metals need to be joined, okay? It's much like your car battery. Between the positive post and the negative post is the potential, right? But nothing happens until you turn the ignition in terms of electron flow. The same holds in a hydronic system. Acceleration factors, now in this case, galvanic attack, acceleration happens as a result of having low pH and low alkalinity, or both, okay? So those determine the rate of a galvanic attack. Now speaking of the galvanic series, you probably have seen this before, but if you look at the various metals available, starting with your very noble gold, graphite, silver, and then starting to get into metals that you see in hydronic systems, stainless, they're at the top of the chart, very anti-corrosive. And at the bottom of the chart are the metals that are less susceptible to corrosion, magnesium, tin, zinc, aluminum, etc. And in between are all the other metals that you typically see in a hydronic system. The brass-based alloys of bronze and brass, the copper-based bronze and brass and copper itself, and then filling it out, steel, iron, etc. So the further away a metal is on this chart, and if they're connected to one another or by way of another metal still connected, you have the effects of galvanic corrosion that can take place. So if we use as an example copper, which is a typical plumbing product, right, and zinc, and look at an experiment that you can do today. Hang on a second. Lost my place here. You could take a multimeter, a voltmeter basically, a little experiment, take a beaker, on one connection put a copper penny, on another connection a zinc coated nail, and dip them into tap water, not to be confused with water, tap water which has minerals. You can see that you will induce a voltage of 0.875 volts in this experiment. So basically, setting up the effects of galvanic attack. Now, if we were to join those metals, they would start corroding. If we repeated this experiment and replaced the tap water with demineralized water, our voltage would be either eliminated or greatly minimized. So here's a shot of the effects of galvanic attack in a heating system. This is iron that has basically been pitted. It's sacrificed to some other noble material inside of the system. So let's take a look at a system. Here's one. You can look at it real quickly. There's a few things, and we'll come around to some of these components. But first of all, here's a couple of decouplers here. They're not Caleffi hydraulic separators, but we'll be talking about hydraulic separators later in this presentation. But the thing to point out is the piping. This is, I believe, aquatherm piping. It's plastic piping. So what does that do with corrosion? Well, it does help the issue of corrosion. You don't have any effects of galvanic attack from, say, flow from this air separator to these pumps or to the boiler. You have basically an insulation going on. Now, does that stop corrosion from happening galvanically? No. Within each component itself, you could get corrosion amongst the different materials within that component. So as an example, if you took our air separator that you just saw in that last slide and looked at the inside, well, kind of the working end, if you will, the business end of an air separator is its mesh. And one of the things that we do with our commercial meshes, we use stainless. And if you remember from the galvanic chart I showed you a few slides back, very, very noble, and it won't succumb to any type of galvanic attack. Other makes have been out there that use plated metal of some sort, less noble and potentially less withstanding of galvanic attack. So both galvanic attack and limescale is largely a function of the quality of the water that you put into your system. In fact, almost entirely. So here's Bob filling up a solar thermal system, okay? And if he were to fill this system up with water that was having minerals in it, basically hard water, okay, well, does he still have a problem with perhaps scale forming or corrosion forming? Well, it depends on the pH and the alkalinity, and this is where the two interact with one another. And this is the Baylis curve. Now you can look at this curve and you can tell it's been around a while, right? You got kind of squiggly lines. In fact, if you Google Baylis curve, you'll see it on all kinds of websites. I pulled it from Mountain Empire Community College. I honestly don't know where that college is. I hope it exists. But in any event, it's a true chart. And so let's say in our system, we filled up our system. Say we had some groundwater, which would maybe make the system a little bit high in pH. And let's say we had a 7.5 pH reading on our groundwater. Now, are we going to have a problem? Well, not necessarily. If our alkalinity is between 75 and 200 parts per million, we're actually still in a safe zone. So we don't necessarily have to condition this water to try to bring it into that safe zone, which is what a lot of the chemical companies do. They try to adjust your pH and your alkalinity to bring it into that safe zone, as well as add binders and things that keep things from coming into solution and going out of solution. Okay. So if you look at water, and this isn't a chemistry exam, but just looking at water from an untreated standpoint, basically water that has minerals, softened water, and demineralized water, what happens is these brown little particles indicate hard water, basically calcium and magnesium, and the blue would indicate any other type of mineral or salt. So untreated water has these. And as a result, left untreated, it will set up the effects of galvanic corrosion and limescale formation in your system. Now, you can take that hard water, if you will, and soften it. Now, are you out of the woods for corrosion? Well, partially. You've gotten rid of largely the limescale formation problem, but when you soften water by using the ion exchange process, you're really leaving behind salts. And salts keep that water conductive, making it still an electrolyte. So we still have the issue of galvanic corrosion that we have to contend with if we're only going to put softened water. Now, if you demineralize the water, which pulls out all minerals, you have basically pure water, in which case you don't have the effects of limescale or galvanic corrosion. And this quick matrix is a kind of a quick guide here. Starting at the top, if you have untreated mineral-laden water, your risk of limescale is going to be high and corrosion for galvanic attack high, as we showed. You can soften it. It will reduce, in some cases, even dramatically, your chances of limescale, but it doesn't too much improve your risk of corrosion. Now, you can after you fill the system after a softener, you can put chemicals in. Now you have taken your risk of limescale and corrosion down quite dramatically. The important thing is to make sure that you check those the pH level and alkalinity of your system to make sure a year later and a year later and a year later that they're in the desirable range. And then lastly, and perhaps sometimes the most expensive way, is to demineralize the water, either through a distilling process or a demineralizer. Now, we mentioned glycol. How about using glycol with antifreeze? Very common with systems in the United States and Canada. Okay, so here's a geothermal system being filled with fluid. We recommend inhibited propylene glycol, not uninhibited, but inhibited propylene glycol, and mineral-free water, not untreated water. Because if you use untreated water, say well water, with even inhibited propylene glycol, the glycol basically the inhibitors can break down. So don't do that. And Jeff Persons, our friend who showed us in a couple of webinars ago, showed a quick experiment. This is a beaker that has a steel wool in it, and inside of the beaker is 80% water, demineralized water, and 20% propylene, inhibited propylene glycol. And 6 months later, this is what you see. Basically, nothing going on, protected. Now, pull the demineralized water out and put in place well water, repeat the experiment, and here's what you get 6 months later. You can see the steel wool starting to break down. It's oxidizing. And down here in the bottom of the beaker, you can see the inhibitor starting to precipitate out, basically rendering the antifreeze characteristics of your glycol to protect that geothermal system or that snow melt system from the effects of freezing. And that's a really bad problem. Okay. So in the end, if there's questions, consult your chemical treatment provider. In the case of here in Milwaukee at the Caleffi headquarters, we actually have a chemical feed on our system to keep those chemicals in balance so that we're in that zone where we don't get galvanic attack or limescale formation. So that leads us to the third of the three areas of dirt, and more the classic case of dirt, oxidation of metals, I mean, and that's through a chemical oxidation. And the required conditions in hydronic systems, first of all, you have to have air, and then you have to have metals that react with air, whether it be iron or steel or aluminum. And to see some examples, here's a boiler that has failed,
pulling out the water tube. You can see it's completely plugged with what we can see as iron oxide from our friends down at GOES in Houston. Here up in Indiana, a cast iron boiler that ultimately it started to lose its efficiency, becoming less and less efficient. And eventually the cast iron section cracked. The section was pulled out and liquids inside. This is in a dried state after it's been sitting around a while. And we can look at this, and we can see by the way of the colors here, there's a lot of iron-based particles in here. And if we took a magnet and ran it across this basically debris here, it would, the magnet would pull up a lot of those particles. And more on magnets here in a future part of this webinar. This is just a scary story. Here's a section of a condensing boiler with the plate pulled off, and you can see what's going on. It failed. And if you look real closely, you can see water that's actually spurting out of the copper tube there. Now, whether this succumbed to the effects of rust, basically, or if it was a combination of rust and limescale, it's hard to say. But in the end, it created dissimilar stresses on that, and it failed. And here's another heat exchanger, different type, another very good heat exchanger, but with the inappropriate water conditions and treatment of air and dirt in the system, a failure. And lastly, dirt, as we know, can create other problems in the system, such as erosion and control valves not working properly. So in order to rust, we need air. So where does air come from in a system? Well, if we have a radiant system, our PEX may or may not have oxygen barriers to prevent oxygen from migrating through the section of the pipe. If it doesn't, even though you might expel all of the air out of the system, air will continue getting in by way, or oxygen, if you will, by way of osmosis, basically through the pipe walls. And then, in general, anywhere you have a connection of a part to another part is a source for air to get into. Maybe not very quickly, but if fluid can get out, assume air can get in. And that becomes especially pronounced as the system begins to age. So as our systems get older, parts start wearing, air vents start losing, in some cases, water. Pumps can start bleeding water through the flanges. We can get rusting on some of our system from improper insulation that could cause eventually a little bit of water leaking out. Now what happens when that water leaks out? Well, the system's going to want to lose pressure, right? But the makeup system is going to make sure the pressure stays up. So as your makeup system works, the water from the source of that makeup is typically laden with what? Air. And it's another source of getting air into the system. To do what? Create the problems that we've been talking about. I show an expansion tank right here. As that expansion tank starts to age, that bladder starts to wear, starts to become what's called waterlogged. The acceptance volume is going to become reduced more and more, and introducing more and more water into the system as the makeup tries to keep the pressure on. And that's not so readily identifiable by looking at it versus some other components. So even aging expansion tanks can cause air to get into a system. So as designers, we want to get rid of all this air regardless of where it comes from, and we need to be knowledgeable that air comes into a system or exists in a system in three different forms. Air that's stationary, basically it forms and goes to high pockets in the system, whether it's the top of a riser or top of a buffer tank as an example. Air that's in the form of microbubbles, and air that is actually dissolved within the water. Now, as it relates to the efficiency of the pumps, we don't care if air is dissolved. If it stays dissolved, we don't really care. Water is incompressible. The problem is as water undergoes pressure changes and temperature changes, it will come out of solution, and it will end up as a microbubble, and those microbubbles will accumulate and end up as air pockets. That's kind of the migration of what happens in a system. So dissolved air in water, how does it perform? Well, water's ability to hold air is, one, proportional to pressure. Okay? Water's ability to hold air is proportional to pressure. The more pressure you have on your system, the more that system will keep that air in check in solution. Okay? And it's inversely proportional to temperature. So proportional to pressure, you can picture, well, the effects of that, you take a bottle of beer, the beer's under pressure, you open up the cap, and all of a sudden you see gases come out of solution and bubble up. That's basically that phenomenon. The inversely proportional temperature is you basically take a pan of water, put it on your stove. You don't see any air bubbles, but you bring it up to a boil, and basically that air is basically coming out of solution. So with that, here is in a hydronic system how water and air react together or perform together as it relates to how much air is dissolved in that water. So on the x-axis is the water temperature in your system, starting at freezing, going up to 345. And the y-axis is how much air is in your system for every 100 gallons, okay? And these red bars are basically isopressure bars, and we'll talk about that in a second, okay? So how do we use this, and how do we apply this to our designs? Well, let's say that we have a heating system. You have a boiler, you put it into the mechanical room, it's going to deliver heat first, second, third, and fourth floors up. Okay, you install the boiler, you design the system, and you have specified that at the boiler you want 30 psi of pressure, okay? And that would be represented by this point here. Now this is 30 psi of absolute pressure, which means 15 psi gauge pressure, okay? Now, and nothing's happened. You haven't fired the boiler on yet. All the air is out of the system, and you're just getting ready to fire the boiler on for the first time. So we're at basically room temperature, 65 degrees, 30 psi. At that point, before anything happens, that water sitting in that boiler has 3.6 gallons of air for every 100 gallons, okay? A lot of air. Now let's simulate that we fire the boiler on for the first time and show this effect of air coming out of solution. As water heats up, it wants to do what? It wants to expand, but you have put an expansion tank on your system, so the pressure isn't going to change. So as you heat the water up from 65, let's say we're going to heat it up to 170, not an untypical temperature, we're just going to ride right down this curve to here, at which point the amount of air that's in solution now is 1.8 gallons. We started at 3.6. We lost half of our air. What happened to the air? It came out of the solution. It's running around in the form of air bubbles and eventually air pockets. Now, we haven't left the boiler yet. We're going to send that water and show the pressure effects of air and water. And let's say that we send that up 4 floors, which is about 15 psi. We drop down to here. And as that water goes up to those heat emitters on the 4th floor, we only have 0.6 gallons of air for every 100 gallons. So we lost 3 gallons. It's racing around only to want to create problems, noise, corrosion, to name a few, air locking of pumps and the like. So we want to get rid of this air. So knowing this property of air, and we take our hydronic system, a very basic system. Let's say it's a heating system. We have a high mass boiler here, and we have a pump and some zone valves. And then let's say it's all on one level. Where would we put our automatic air separator? Well, we know that where the temperature is hottest is where these are most effective. And coming off your boiler before you start sending it to your zones, that's hot. But is that the best place? Nope, because it's also the highest pressure. In front of your pump on your system, or a pump, is always the highest pressure point in the system, and behind the pump is always the lowest pressure point in the system, okay? Pumps create head, everything else steals head. So a better place to put our air separator to work most optimally is where the temperature is highest and the pressure is lowest. Now we've optimized that air separator, okay? Now speaking of pressures, what is the pressure in the system when that pump fires on? We don't know because we don't have an expansion tank on here, right? The expansion tank is always your reference point. It has a compressible diaphragm in it, if it's that type of expansion tank. And as a result, as that pump fires on and off, or even multiple pumps firing on and off, the pressure at which that expansion tank joining to the system started with before the pumps were on never changes. It's the point of no pressure change in your system. So why is that an issue? Well, let's say this expansion tank in your system was the starting pressure was 20 psi. All right, nothing's turned on, and you put 20 psi. And this pump is capable of generating a 30 psi head. The expansion tank is going to maintain 20 psi, and that pump's going to generate 30 psi, which will do what? What does that cause? Well, it's going to create a vacuum on the backside of this pump. All right, and air separators such as Caleffi's or anyone else's, they work under positive pressure. So as air bubbles accumulate, rather than being vented out, if we got negative pressure, we'll suck air in and cause a problem with the pump, okay? At worst case, calls it the airlock and fail if it doesn't have any temperature protection device. So a better place to put it is behind the pump. So always pump away from an expansion tank. Or we could put it down here because there's very little difference in pressure drop between here and where we had it before. Now what if we waterlog the expansion tank? Well, it's basically similar to as if not having an expansion tank at all, right? And we could have air come into our air separators. So Caleffi offers a anti-siphon air vent cap to protect this from actually happening. So a little protection. And here's our mechanical room actually right here in Milwaukee where you can see basically our little protection cap. Under pressure, it vents out air. Under a vacuum, it prevents air from being sucked in. So even if you forgot to open up your isolation valve on your expansion tank, it protects air from in this case, causing that Bell and Gossett pump to airlock, keeping it working effectively. Okay, back to our system here. We're all on one floor. Let's talk about hydrostatic effects of air. Let's get rid of these 3 heat emitters over here and simulate the effects of going up with our water in our building. So if we do that, we have first floor, second floor, third floor, fourth floor, and we're sending risers up there to send heat to these panel radiators or whatever type of heat emitter. This is where you want to put air vents. And air vents, automatic air vents, like to be operating under pressure. So to make sure they have positive pressure, in the case of Caleffi, like 5 psi minimum, 10's okay too. In fact, you can go as high as you want as long as you stay under the operating pressure, maximum operating pressure. So as the designer, to make sure you get 5 psi at the top of your system, down here where you pressurize the system, you would do what? Well, you would basically designate that gets pressurized at 22 psi. That would create 5 psi up here. And next month, Bob will be talking about the whole filling and purging process, and I'll skip this and let you dial in next month to listen to that whole process of filling and purging and setting pressures with your pressure reducing valves. Now, speaking of air vents, here's some of our air vents, and I won't get into the details. Whether it's a Caleffi air vent or an Amtrol air vent or an Xylem or B&G, pick your brand. They operate very similarly. If you cut away that air vent, you have a float, and the blue indicates the water level, and the white indicates the an air column. In this state, nothing's going on. The float is not sending air out of the system. What happens is air bubbles go into the float. This air column starts to increase, which drops the water column. The float drops with it, and because it's hooked to a pivot arm, this little needle valve pulls down, and eventually you have released the atmosphere of the air. It pushes the air out, the float goes back up, and that process continues over and over again until all the air is out of the air vent. Now, the 2 things to remember about air vents, maximum venting pressure, that's the pressure at which the air vent will cease working, because the pressure times the area on the bottom of this pin indicates the upward force. If that gets higher than the weight of the float, then regardless of how much air gets built up here, you won't vent air. And air vents are rated from anywhere from 35 psi to 120 or something like that, so just keep that in mind. Also the discharge capacity, so how much air can get out of that air vent. So here's one of our charts, and so as an example, in our high capacity air vent at 60 psi, it will rid itself of 6 cubic feet per minute. Now this little guy down here is worth talking about, and this is a hygroscopic air vent. And why is it worth talking about? If we go back to our diagram here where we had these float type air vents, what are they trying to do? They're trying to get rid of the air that goes up in the riser so it doesn't create havoc in our heat emitters, okay? Alternatively, we could have gotten rid of those floats, okay, and right on the heat emitters themselves put in a air vent such as this. Now, what is this air vent? It's actually an automatic air vent that relies on hygroscopic sponges, if you will, to cause it to operate automatically. So here in the automatic mode, we can see if we get a buildup of air underneath our air vent on our heat emitter, all right, the air, because the system's under pressure, will push the air up through these series of sponges. They're actually little discs, and there's spaces between these dishes when it's in the dry mode, pushing the air out. And after the air is expelled out, if moisture comes in behind it, the sponges absorb the moisture, they swell up, and they close off any further passage, and thereby acting automatically. Next time air starts to accumulate here, they dry out, and it repeats the process all over again. They also can be operated in a manual mode by just spinning this cap counterclockwise. Here's a shot of what that dry disc looks like, these series of discs, these sponges, and then as they get wet, they expand quite a bit. And Hot Rod in the earlier training webinar showed a dry disc and a wet disc to show you that basically phenomena. And if they ever need to be replaced, the nice thing is there's a built-in check valve here, so you can spin the cap off and within seconds literally replace that cap. So here's an example of where this comes in handy. This was actually a job where it was a baseboard heating job. In the bedrooms, there was the baseboards were making noise because there was an unidentified source of air somehow getting into the system. And so these manual air vents were pulled off, and these automatic air vents, hygroscopic air vents, were put in and taking care of the problem. Now, the source of air never got corrected, but since then, the issue has been taken care of as it relates to that air getting back out of the system pretty quickly. Okay, let's go back to our system here, and let's take a look at our boiler here. We're going to start talking about some other items. Let's say this boiler wears out in time, and you, the engineer or designer, want to replace it, and you replace it with more modern equipment, say a condensing boiler. Many condensing boilers have heat exchangers that don't contain much water, low mass, okay? Now, where would you put your air separator to be most effective? Well, you might put it right here, because it's the lowest pressure point in the system, right, on the suction side of the pump, and at the highest temperature in the system, on the discharge of the boiler, okay? So everything's fine and happy here except for the boiler. In a low-mass condensing boiler, in many cases, the manufacturers want to maximize the pressure in that boiler. So rather than pump away, they want you to pump into the boiler, because that does what? It takes the temperature at which you can get flashing, and it increases it. And flashing creates what? It causes stress in your heat exchanger, and it should basically reduce the life expectancy of that heat exchanger. So pump into these type of boilers, okay? But now we're pumping into the expansion tank, so make sure you pump away from the expansion tank. Now, the thing about retrofits is that the piping and equipment that you kept in place has already been compromised and quite susceptible to continuing oxidation and rust floating around in the system. So in retrofits especially is when you want to protect your equipment from dirt, such as using a dirt separator, or a combination device that does both air separation and dirt separation, such as this residential one or a larger commercial one. We'll come back to those here in a second. Now, this issue of pumping in and out of a condensing boiler, what's going on? Well, if you take a condensing boiler, and just by a real simple example, if we have our primary pump and we have an expansion tank and the rest of our system here, and let's say that we pressurize the system to 20 psi, and our pump is capable of delivering 25 psi ahead, so going into our boiler is 45 psi. And condensing boilers often have a large amount of resistance in them, which means what? Pressure drop. So coming out of that boiler could be 35 psi, and that continues around through our system, losing the rest of the pressure back to 20 psi, starting the process all over again. So the lowest pressure in the boiler heat exchanger is 35 psi. What temperature does boiling start to happen at 35 psi? Well, we can quickly look at a pressure temperature chart from our engineering tool chest and see that 35 psi, which is 50 psi gauge pressure, will boil at 281 degrees. So our flash point is 281, okay? It's pretty high, actually. If we pumped away from the boiler instead and kept everything the same, we just put our pump coming out of the boiler and our expansion tank behind it appropriately, okay? Our pressures don't change. Our expansion takes 20, our pump will raise at 25 psi, and we'll lose 35 coming around the system. And now our system, our boiler has 30 psi going in and 20 psi going out. Now, what's the boiling point in this situation? Well, we can look it up very quickly, and we can see it's 259 degrees. So we've added significantly protection on that condensing boiler by pumping into it rather than away from it. Here's a shot now jumping to air separators. You can see this was being installed. I think this was up in Montana. And let's take a look at what's going on in these air separators. How do these things actually work? Well, here's the inside of a separator. This is inside of it as a coalescing mesh, basically sharp edges. And as microbubbles come out of your pipe as a result of heating the water or undergoing a pressure drop, those microbubbles, before they have a chance to go back in the solution, attach to the sharp edges. More microbubbles collide with those microbubbles, creating bigger microbubbles. They continue to cling onto the mesh on another point. Eventually, the buoyancy force causes the bubbles to continue going up into the air vent portion of the separator and vent it out per the process we saw a few slides ago. Okay? That's how coalescing works. Very effective at taking air and getting rid of it in a system. Now, before I leave this slide, you can see these little pins here. Our floats are pinned because it's not always very easy to make sure that that air separator is perfectly vertical. So if you have your flanges are a little bit rotated and as a result you're not perfectly vertical, that's okay because the Caleffi air vent riding up and down that pin keeps that pin from getting hung up. Because if that pin gets hung up, the air separator doesn't work. So that's a nice feature of the Caleffi air separators. Let's jump to how you get rid of dirt. Here's a small little dirt separator. Here's another one on a boiler. You can see a dirt separator, so I'm going to guess that this is the intake of the boiler and this is the discharge part of this peerless condensing boiler. And here's another shot of a couple of boilers and protected by dirt separators. I can see up here, by the way, we'll finish this with hydraulic separation, and that's actually a spirotherm hydro separator, just to prove that we don't make all the hydro separators. We'll come back to hydraulic separation in a second. So how do these low flow zone separators work? Well, here's a small one, a residential one. Here's more of a commercial. As fluid comes in laden with debris into a separator, the velocity slows down dramatically. And these meshes are designed to deflect the debris out of the path of the flow. As a result, you end up separating the debris away from the water, not filtering it, but actually separating it away from the flow path. And as a result, you don't get any pressure buildup as it does its thing, as opposed to, say, a Y filter or a basket cartridge filter. Speaking of which, as such, here's a Caleffi Y strainer or basket cartridge filter. We like these, but we like them high up in the system. And if you did a cross-section, this is what they look like. They have a little filter here, and fluid would come in this direction, go into here and back out here, and the debris would catch here. We like these high up in the system, such as air handlers and fan coils, because the higher up in the system you go in your building, the less chance of debris. Debris likes to live down in the bottom of your system largely. So they're a good place for using Caleffi or someone else's Y strainer would be protecting this control valve and the heat exchanger on an air handler or a fan coil, combined typically with a balancing valve. Now these 2-in-1 air separators that we talked about earlier, if we cut them in half and looked at what's happening inside, you get something like this. Now you might ask, well, that kind of looks like an air separator mounted on top of a dirt separator. I don't know what would give you that idea, but yes, shamelessly, basically that's what we did here. And so this is very popular in application because why? Well, a lot of today's equipment versus yesterday's don't like debris, as we saw it. So, and all hydronic systems need air separators. So rather than specify two components doing each function separately, from strictly an economical standpoint, if you look at our list prices of a 4-inch line as an example, your 4-inch air separator is listed $4,200, $3,600 for the dirt separator. The combined one will do the same job for less than $5,000. So not much of a premium over just the air separator itself. So here's some shots of some of these combination 2-in-1 devices. This is from Biggerstaff Radiant Solutions. This is, by the way, here's some closely spaced tees over here we'll come back to in the last few minutes of this webinar. Air and dirt separators on a chiller application. We can see condensing going on in this before they have insulated this job. Okay, so even cooling systems need air and dirt elimination. Here's a big air and dirt separator, and there's hot rod in front of it. And just to point out that we make very large separators, and we also have a lot of education videos, which this is a screenshot of. And if you went to our website and ever wondered what that Panther was looking at on our website, well, obviously he's looking at all of our training videos on YouTube. So a little shameless plug for you if you are interested to take a look at our training videos, because they're very helpful. Bob tears apart product, talks about how it works, et cetera, et cetera. So let's jump to dirt separators, then we'll go into hydraulic separation. Here's a dirt separator, and it comes with insulation as an option, and I don't want to talk so much about that, but what I want to point out is this little black ring. What is this black ring? Well, it's a magnetic collar, and that magnetic collar is actually laden with or has rare earth magnets, neodymium ferrite magnets, the same kind of magnets that are used in ECM pumps, the high-efficiency pumps that are becoming more and more commonplace. So now we have a line of product where we've taken this magnetic effect and we've placed it on the dirt separators. So even that very fine talcum powder consistency ferrous oxide, the result of rusting in your system, rather than allow that to get a chance to go and find a home in the system where it's going to create problems, like caking onto a heat exchanger or getting into a pump, we capture it with these magnetic collars. And so we just introduced this feature not too long ago. They're now getting applied in the marketplace. They're very helpful on retrofits. This is probably a retrofit from up in Alaska, White's Plumbing. And so he perhaps put in some very modern equipment in here to replace maybe the older equipment. That modern equipment you don't want to have caked up with ferrous oxide. We also have ECM pumps here that we want to protect from ferrous oxide. And we have a whole line of these, as you can see, both dedicated dirt separators and combination air and dirt separators that have that magnetic collar. Now,
how does this work? Well, just to demonstrate the effectiveness of magnetic separation, here's our polymer dirt separator. It has the magnetic collar around it. This is actually a hot rod system. He basically opened up the ball valve, purged off some fluid. Mind you, he didn't have to take the system offline. That's the nice thing about our dirt separators versus Y stringers, which you a lot of times have to take offline. You can do it when the system's still running. And filling up that glass with what you can see is very untasty looking water. And he let the debris settle out, and he put a magnet to the side of the glass. In the next slide, we can see what happened. As he puts the magnet into the glass, the ferrous oxide jumps to the magnet. So that's the effect that we're accomplishing by putting these collars on our dirt separators and preventing that debris from getting into other parts of the system and causing problems. So ECM motors are very common. Xylem and Grundfos and Taco and Velo, probably just to name some of them that are in the market, are out there, very good pumps. But what they have in common is they use permanent magnets in the rotor. In the wet rotor, there is a permanent magnet. Rather than inducing a magnetic field into the rotor, the magnet's already there and allows pump manufacturers to get very high efficiency, for lack of better words, if you will. And if you take these rotors out of these pumps, you can see the effect of those permanent magnets. They're extremely strong. Okay, so here we got a couple different pump makes, and Kevin here put tools on it and show basically how strong these are. Really strong. In fact, I think Kevin was missing some fillings that night, unexplainably. So the permanent magnets, that attraction, you pull out a rotor from a permanent magnet that has a lot of ferrous oxide in the system, you might see something like this here, where basically that magnetic field has attracted that ferrous oxide and accumulated on the rotor as it spins around in the volute or inside of the canister here. Now, does that mean that the pump's going to fail? No, not necessarily. Okay, but as as this builds up over time, and if you're working under a delta P mode, that pump is going to maintain your delta P, but it's going to work a little harder, perhaps consuming a little bit more wattage than you'd like to accomplish the flow rate that it was set for. Okay, so we especially like these when you have very efficient heat exchangers and ECM pumps to use this magnetic type of a separator. So sizing separators, all of our separators, we have a quick sizing reference. So our 12-inch air and dirt separators, as an example, 10-inch, 8-inch, down to 3/4 inch, we specify a flow rate through that separator which the air and dirt elimination is most optimized, and even up to the equivalent of 10 feet per second, we indicate the flow rate, which you can take that up to. So they're high velocity rated. So as an example, our 6-inch separator can be taken up to 93.6 gallons per minute, not 904, God forbid, but 903.6. Okay, we're going to finish in pump conflict. We're probably going to go 5 minutes late here, but I think it's worth going through. So how do we eliminate pump conflict in a hydronic system? Well, what we want is demonstrated by this graphic. We have a bunch of pumps that we want to have a certain flow rate. And when one pump turns on and one pump turns on, as they turn on and off, we don't want it to affect the flow rate of part of the system driven by another pump. So if that third pump over here, as an example, turns off, the effect that we want is something like this. We don't want it to impact. Okay, so that's decoupled pump. If we turn that third pump off and the result was something like this, now we have pump conflict. Okay, so what causes pump conflict? Well, I guess I can talk about it by way of some schematics. One way of correcting pump conflict is by way of closely spaced tees. And I'm going to show a few things here leading up to closely spaced tees. Let's say, for example, we have a hydronic system with a heat source, and we have 3 pumps, and these pumps now send heat up to our system, and it comes back. Okay. Now, the flow rate of each of these pumps has to go through the boiler. Okay. All right. And there's going to be resistance in this boiler. So as this pump turns on, comes back around, and wants to go through the boiler, it's going to create a back pressure against these other pumps because there's resistance in the path ahead of it. Okay? Same with these other pumps, they're going to interfere with one another. So one way of preventing that is simply to create a path of flow for these pumps to go without having to go into the boiler. And we can do that such as this. Okay? But by doing so, now we've created a shortcut for the pumps. Now we don't have any way of getting heat from the boiler to our system.
So we have to make sure we put a primary pump in. So now we have closely spaced tees. But they're not really closely spaced because we still have a gap here. When the flow comes here and it wants to figure out, do I want to go this way or do I want to go this way, it will go both ways. There's still going to be some resistance here. So for closely spaced tees to work properly, you need to keep them closely spaced, such as this. So this is a decoupled system here by way of closely spaced tees. Alternatively, we could have taken, instead of closely spaced tees, we could have taken a buffer tank. All right? Like a pair of closely spaced tees, we have 4 ports out to the system, back in from the system, and then the primary side. Okay? We might use this if we need some type of buffering in our system if our zones are highly zoned over here. Okay? Or we could use hydraulic separators such as this. Now, hydraulic separators have a couple other features that closely spaced tees don't have, and that's air elimination and dirt elimination. Now, let's take a look at take a look at hydraulic separation here. But first, closely spaced tees. Now, I didn't get a chance to talk to Michael Cummins here, but I really like this job that I found. I like it even though it doesn't have a stick of Caleffi on it. It's very good, but it's also a good place to talk about closely spaced tees. So here's his primary loop, and he's using closely spaced tees right here. Okay? And what he's done is follow the rule of making sure your tees don't exceed 4 times the pipe diameter of your pipe. If instead of connecting here, he decided to connect here, that spread would cause these pumps to interfere with one another. Okay? So keep them close together. A hydraulic separation, or a buffer tank used to hydraulic separate it, is done here in this shot. So here's a buffer tank, and we have 4 ports, 1, 2. This is our secondary side, a bunch of pumps sending heat. And perhaps this is a heat pump system, perhaps chilled water up to our system. And connected to our buffer tank, our heat pump, is our primary side. So we don't have any interference on our primary pump. This is a Caleffi buffer tank, which has also the added feature of additional ports on the side, enabling a combination system. So this contractor, in fact, they'll be on board with us, I think, on our next webinar talking about this system, Prestige boiler as backup in those cold winter months when they need added heat versus what the heat pump can do efficiently. Now lastly, hydraulic separators, and we'll wrap up. Here's a hydraulic separator shot. This is a commercial job, I believe from New York, courtesy of Lars. Thank you guys. Here's another shot down in Texas, getting wrenched in. You can see a hydraulic separator. Here's another one. Here's another one. I'll just go through these real quickly in the interest of time. Here's one that we had going up to northern Wisconsin because there's a professional football team up there that we thought we could do some dual branding with. And, well, we found out that we really couldn't afford to do that dual branding. We can't say their name on that practice field. So we call it the Northern Wisconsin NFL football team. But I tell you, the system is very packed with features. Okay, I'm going to speed through this chart quickly, but to show you kind of the engineering side of what happens with pump conflict. Here's a system. It's a boiler, high-efficiency boiler, and it's got 2 pumps, and it's all on one level, and these circles are pressure gauges. We're just going to pretend it's all on one level, and everything's off, okay? And the engineer has decided to pressurize the system to 12 psi. So everything is 12 psi. We're going to demonstrate the effect of back pressure, what causes pump conflict, and use some values here. There's going to be a call for heat on this big pump driving heat in this zone over here. It's a 2-zone system, okay? We're going to find out what happens. So take a look at what changes as far as the pressure in our system. Everything's 12 psi to start off with. Now, this is a heating system. We could have been talking about a chilled water system. The mechanics are exactly the same. So we'll stay with heating. There's a call for heat. The pump fires on, and let's find out what happens to our pressure. Now, remember I told you the reference point to start calculating pressure is your expansion tank, not calculating, but what actually takes place. We start off with 12 psi, and that's where we start off here, 12 psi, and assume there's very little pressure drop through our headers over here. So going into our pump is 12 psi. Our pump raises it 10 psi of head, so we got 22 psi on this gauge coming out. We're delivering heat to our zone. We're coming back around. We get to this T here. Now the water wants to go somewhere. It can't go this way because we have a check valve on the top side of this pump, okay? So it continues on its flow, losing pressure through the heat exchanger of the boiler back up to 12 psi, okay? All right, everything's fine and dandy. Everything's happy so far. People are getting heat in this zone. there's going to be a call for heat on this second zone. Now, before there's a call for heat on the second zone, let's see what happened here. When we came back around here, we had 17 psi, which means we had 17 psi. We had to continue around. We got to here, we have 12 psi, which means we have 12 psi here. 17 psi, 12 psi. We have created a 5 psi back pressure on this second pump that hasn't even fired on yet. And if that pump has been designed to deliver 3 psi ahead, guess what? It's not even going to be able to generate any flow. Okay? So that's a problem. So how do we fix that? Well, we do a couple things. We put a hydraulic separator in our line. By doing that, we create a bypass, if you will, or shortcut for our secondary pumps to send flow. Okay? But now we've cut off flow over here, so we need to put on a pump, a very small pump at that, because it's only worried about sending flow here. And the last thing is we want to make sure our headers are designed for the velocity to be more or less under 4 feet per second. If they're a very long length of pipe, maybe 2 feet per second, short length of pipe, maybe 6 feet per second. But use 4 feet per second as a rule of thumb. By doing so, we have decoupled this pump. And now we can see what the effects are on the pressure. Okay, so we start with our expansion tank. Now, with the hydraulic separator, we can put our expansion tank basically anywhere around the hydraulic separator because there's no pressure drop around the hydraulic separator. Okay, so let's say we put it here. So 12 psi is the starting point, right? Which means basically this is 12 psi. We raise our pressure 10 psi, come back around from 22 coming off the pump, back around to 12, okay? Now at this point, there is essentially no pressure drop from this point back to our pump again because we've gone through our header that has very low resistance because we kept it under 4 feet per second velocity, and our hydraulic separator has no pressure drop, okay? So there's no difference between pressure here and here, thereby creating no back pressure on our pump. That's how hydraulic separation prevents decoupling of pumps. Now we could have, and then if our second pump turns on, it turns on without impacting the flow rate on our first pump. So they're completely decoupled from one another. Now we could have now, with the appropriately sized hydraulic separator, put a whole bunch of pumps over here, okay? And they'll all be decoupled as long as we follow those rules. Similarly, we could have multiple boilers over here. Or if it's a cooling system, we could have several heat pumps or chillers over here, as long as they're got the appropriate sized headers and appropriate sized hydraulic separator. Okay? Now, before we put that hydraulic separator in and we sized that pump, we were sizing it to go through the common piping running through the boiler. And if we looked at the curve representing the resistance in this circuit here, we might have gotten a curve like this, and perhaps the flow rate that we wanted, we would have chosen a pump such as this. When we introduce a hydraulic separator now, it changes things. That curve now has been flattened out because what? We've reduced the resistance that pump has to see, okay? So rather than flowing here, that same pump would cause it to flow here. So hydraulic separation also enables smaller pumps to be used most optimally. So how do you size a hydraulic separator? It's very simple. You take the maximum flow rate under design conditions in your primary circuit, maximum flow rate in your secondary circuit. The greater of the two determines what size hydraulic separator you use. So as an example, if we had 140 and 230, that would put us into a 4-inch hydraulic separator. What's going on in the inside of these separators? If you peel them apart, here there's no moving parts. If you peeled it in half, this is what's happening. Here's a baffle plate. Now, the baffle plate is in there as a flow straightener. Why? Because when you have pumps turning on and turning off on your secondary, and perhaps one or more pumps turning on and off in your secondary, you're going to have almost always different rates of flow on your primary versus secondary. So if your primary has more flow than your secondary, there's going to be a flow component going down from the boiler back to the boiler in this direction if you have a heating system. Same thing on the secondary. If your flow rate in the secondary is higher than the primary, even momentarily, your flow rate will be up this way. So the baffle plate becomes a flow straightener. It takes what otherwise would be turbulent flow and makes it laminar. Turbulence equals pressure drop, which is what we don't want. We want to make it laminar. Furthermore, the baffle plate has been perforated, and that creates that sharp edge effect we talked about. So we get coalescing here, and we get air coming out of solution, or microbubbles getting pulled out and vented out. So we get some air separation here, and we get some dirt separation here. So the primary function of a hydraulic separator is to, decouple pumps and hydraulic separation. Secondary functions are air and dirt. Now the question is, okay, can I put the Caleffi hydraulic separator in and do away with my spirotherm air separator or my Caleffi air separator or what have you, or my dirt separator? Well, it depends on how much air and dirt you have and how much you want to get rid of as a function of time. However, we have introduced a couple years ago another line of related product. It's a hydro separator where we pulled out the baffle plate, and throughout the internal part of the separator, we have included a coalescing mesh, okay, a little bit differently designed. And as a result, we get high efficiency air elimination by coalescing. We have the same level of dirt elimination capability as a dedicated dirt separator, and we get hydraulic separation. So all three functions are available in the HydroCal. So as we've introduced this, why does it make sense? Well, it's the same argument as we showed in the 2-in-1 device. The 3-in-1 device is very economical. Even if you aren't worried about dirt separation, you simply want to do hydraulic separation and air separation, economically you can justify using a 3-in-1 device in place, and you get the dirt separation to boot. So if you look at some of the manufacturers of boilers and their schematics as an example, and some of these are maybe perhaps old, and this is picking an example, I pulled off some of the other extraneous information, but you can see wide strainers to protect the boiler. You see closely spaced Ds, you can see air separation. If you used a 3-in-1 device, you can do away with those closely spaced Ds and their connectors. You can do away with the air separation device. You can do away with the Y strainers. So economically, it makes a lot of sense, and it gives good high performance. So stepping back in time as an example where this system out in Maine had a hydraulic separator, this is before we had the 3-in-1 device, that engineer wanted to have a dedicated air separator also added to it. He could have eliminated that device by using the 3-in-1 device. Similarly, here's a job, and I talked to Warren Air. I love this job. You can talk for an hour on this. There's a lot of good lessons in this. As an example, we have three very efficient boilers here. They're being protected by Y strainers. Okay, so we protect those heat exchangers. Up here is our primary, secondary Ts, a couple of closely spaced Ts, and an air separator. All very good products, and this is a fantastic installation. Alternatively, using a HydroCal, a 3-in-1 device, could have given an option for the designer to perhaps, instead of using closely spaced Ds, use the HydroCal and not having the Y strainers, because the dirt separation capabilities of the HydroCal would do that, and also the air separation being handled by that one device as well. So an example of where it could be applied as an alternative, such as this job up in Colorado where they used the HydroCal as a 3-in-1 device, eliminating those other pieces of equipment. Another recent example is down in Texas. This is at Cisco Foods. This is a HydroCal 3-in-1 device. It's been insulated up here, and this is a bank of 5 boilers. Mind you, these aren't the same kind of boilers. 3 of these are, I believe, condensing boilers, and 2 of these are non-condensing boilers. Maybe it's vice versa. In the south of the United States, where you don't have high heat loads, perhaps a school in Houston, in the morning there might be a slight heat load, and it doesn't make sense to fire on a high-mass boiler, a non-condensing boiler. You want to maximize putting your condensing boiler, so base load with your condensing boilers, and in those peak seasons where you have the most load, bring on your high-mass boilers. So a great opportunity with the HydroCal to combine mixed boilers. And lastly, with the last couple of slides here, the HydroCal is only available from 2 inch and up. So what's the question? The question might be, well, how about 2 inches and below? Well, we introduced for the smaller jobs a HydroCal, if you will, with the added feature of putting the magnetic separation function in place. So it has 4 functions, so that's why we call it SEP4, so separation 4. And this is all the same product, just this is an animation, and this is actually a demonstration cutaway. And so we could have taken this product and talking to Will Atwood up in Wasilla, Alaska, or over in Wasilla. I say over in Wasilla. I sound like it's down the block here. Given that it takes 4 hours to get from Chicago to Seattle and you're only halfway there, it's a little more than down the block. But anyway, talking to Will, who did a really nice job here with this installation. If he had a SEP4 as an alternative, you can see his closely spaced Ts that he could have not used. He could have, in the connecting device, his air separator and his Y strainer, and in place use the SEP4. So I've come to after our time here, and I thank you for your participation. If you have questions, send them in. Hopefully we have made a lot of these issues no longer gotchas for you. Starting next month, Bob will be back here talking about filling and purging. And then August 22nd, we have a guest speaker, Danny Gao, that will be talking about anatomy of a geothermal heating system. And so that will be very interesting. Today's participants will be given a certificate of completion from us automatically. If you have a request for this webinar in hard copy, give us a shout. We'll be happy to give you a PDF. And lastly, if you missed the webinar, as I mentioned, we have 50 of them, now 50, soon to be 50, online for your future reference. And don't forget to follow us on Twitter. We have quite a few followers now versus just a few months ago, and a lot of good information, stuff that you don't see on our website and elsewhere we send out on Twitter that I think you might find very interesting. So again, thanks for your audience, and we'll talk to you again.